Hello everyone and welcome back. So we're working on a second example. Once again, we have an inclined plane here, 40 degrees. What it tells us is that specifications for this 6-inch by 6-inch square post, squares can be helpful there, require that the normal and shear stresses on plane AB not exceed 800 psi and 400 psi respectively. Okay, so 800 for normal, 400 for shear. Now that makes sense because, the maximum shear stress is always half the normal stress, so this should work out pretty well. So determine the maximum load P that can be applied without exceeding the specifications. Now we have several equations here, that using the shear stress equations as function of angle are going to be very helpful for this. Remember, we're solving for P. We don't know what P is. So with that in mind, go forth, see what you can do, see if you can solve this. And if you can't, come on back, watch the rest of the video and we'll do it together. So you have 3, 2, 1, and let's go. So the general equations for the normal and shear stresses that we got were the following. Got my nice shear stress right there and my normal stress right here. Now, hopefully you remember where we got this. It was because we calculated, okay, what was the component of the normal stress? Normal stress is equal to P over A, but then we changed the area. Well, was it? Oh yeah, it's A divided by cosine of theta now. And we had the component of P that was in the normal direction, so that was P cosine of theta. And then that simplified over to here. And something very similar in case for the shear stress. So, because of that, we have these two equations, which makes things a lot easier for us. But we have an issue. This is not at the maximum for the shear stress, it's not at the maximum for the normal stress, it's somewhere in between. And so we're going to have to figure out which one of these cases gets hit first. Will they reach the maximum normal stress before they reach the maximum shear stress, or vice versa? Because just at the, at their individual maximums, yes, the normal stress is always, the shear stress is always half of the normal stress. Doesn't mean that that's the case every single point along the way. So let's get working on that. Now the cross-sectional area of that post is going to be 6 times 6. It's going to be equal to 36 inches squared. And we'll see later what the new plane's area is. So if we really want to figure this out, what we can do is we actually don't have to worry about calculating the new area at all. I'm being silly, because you look right there, that is not the new area, that's the old area. We're able to simplify it and get rid of our calculation because we just did it in terms of our original area. So now we have to solve. We solve and say, well, this P, it has to be less than or equal to whatever this number is right here. And we plug in 800 psi into our equation. Plug in our angle, we plug in our area, plug in the 800, and we get a value. Now this is not the answer necessarily. This is just one value. This says the maximum force so that you won't exceed 800 psi in the normal stress. But we might have at this point already surpassed what the shear stress could hold. So we have to check both conditions. So let's check the shear stress and see if it would have hit its maximum first. So we have a very similar equation. We have just rearranged things again. So we had before that the shear stress was equal to P over 2A times sine of 2 theta. And then all we did was we solved for P. So multiply the shear stress by 2A, so 2A tau nt divided by sine 2 theta, sine of 2 theta, and that's going to be equal to our load. Now we want to make sure that our load is less than or equal to whatever this value is. We have to be careful. Let's check it and see what it's going to come out to be. And it comes out to be 29.2 kips, or 29,200 pounds. And you see that this is significantly less than we had before. The P max for the normal stress, was 43,000 pounds. That was for the shear stress. Oh, sorry, dang it, I want to say the wrong. The normal stress. So what we see here is that we could not use this condition. It would fail way earlier than we would think. So we have to use the weaker condition. This one is less, and therefore that one would be the controlling condition. And our answer would finally be that Pmax is 29.2 thousand pounds. Okay, so just a brief recap. We know what the max normal stress and shear stress can be, and we use both of those to calculate what P would be for those two cases. However, what we realize is that the P for one is not going to be the same as the P for the other. We have to take the smaller of the two. So we solve for P in both cases, we figure out what the force was, and then we plug that into our equations. What we found out in the end was that the shear stress would be the controlling factor at this angle. Not necessarily all angles, but at this particular angle. And it would have a maximum force able to be applied to stay within the limits of 29.2 kips, or 29,200 pounds. Okay, thanks for watching, and I'll see all of you next time. Bye-bye.